On the 18th of November 2025, Google released Gemini 3 Pro, a new generation AI model. As expected, it instantly climbed to the top of virtually every public benchmark. But what mattered more wasn't the rankings. It was the feeling. Even people who had never cared about leaderboards or technical metrics noticed the difference. With a single prompt, the model could generate a fully playable 3D minigame in under a minute. No coding, no engine setup, no technical background. More complex projects took longer, maybe an hour. But the barrier had clearly shifted. I noticed it personally. Tasks that previously required careful step-by-step reasoning suddenly felt lighter, faster, more fluid. The release was significant enough to trigger a reaction across the industry. Inside OpenAI, Sam Altman reportedly declared a red alert. Projects like Sora were temporarily paused. Resources were redirected. The race accelerated, not just for better models, but for better ways to work with them. Then, just days later, Google released Nano Banana Pro, an image generation and editing model. The base version had appeared only 3 months earlier, already showing how radically neural networks could transform images. The Pro version crossed a psychological threshold: ultra-realistic photos, manga recoloring, comic generation, restoration of damaged or lost images. At this point, confidence in the origin of any image quietly collapsed. You'd need real imagination to fully exhaust what the model can do. And that's the key word here: quietly. This is the moment when AI stops feeling like an interesting toy and becomes a serious, everyday instrument. And it doesn't arrive with fireworks. It never does. There was no single day when computers became mandatory in every office. No clear moment when the internet stopped being a playground for enthusiasts and became useful for ordinary households. No one remembers the exact day life without a mobile phone became uncomfortable, then impossible. These transitions are always smooth, gradual, inevitable. And the same thing is happening right now with artificial intelligence, no matter how loudly some people deny it, especially when you remember just how recent this all is. ChatGPT entered public use only 3 years ago in November 2022. 3 years, and we are already here. About a year later, experts began to openly discuss a far less pleasant issue: data, or rather, the lack of it. The most advanced models had already absorbed nearly all publicly available text on the internet. And yet, to keep improving, they needed much more. Not just more data, better data, richer data, structured, high-quality information that simply doesn't exist at scale. The second headache was even more tangible: computing power, data centers, electricity, cooling, infrastructure, or, more precisely, the growing shortage of all of it. We won't dive into who is solving these problems and how that's a separate story, but the underlying pattern is clear. When research and development accelerate this fast, technological and resource limits appear very quickly. 2 years ago, people were already talking about an approaching ceiling, about an AI winter, about a bubble that was about to burst. So far, none of that has happened. But that doesn't mean the problems aren't real. They are. And that's exactly why some companies have already started looking for ways around them. And I found a few of these approaches interesting enough to make this video. I didn't start with Gemini 3 Pro by accident. That release was followed by a series of interviews and statements that quietly outlined a possible future trajectory for AI. One of the most notable was an interview with Ilya Sutskever. It's worth recalling who he is. Sutskever is one of the founding figures of modern neural networks and one of the architects behind OpenAI itself. In 2024, he left to create his own company, Safe Superintelligence. Its work remains almost completely opaque. Since then, Sutskever has rarely appeared in public, so any interview with him is an event. Nothing radically new was said outright. No dramatic revelations, no loud predictions. Overall, the interview quietly confirmed the very problems we've just outlined. Sutskever's position is clear. For the past few years, tech giants have advanced their models primarily by pouring ever larger volumes of data into them. That strategy worked until it didn't. The data is running out, and almost everyone is now using roughly the same approaches. According to him, the next stage will force market leaders to return to something far less scalable, but far more important: fundamental research, new ideas, new principles, new ways to unlock a qualitative leap without simply adding more data and more compute. One of the possible directions he hinted at is continuous learning systems that don't freeze after training, but keep learning dynamically, more like a human mind, adapting, updating, correcting themselves in real time. Around the same time, Demis Hassabis gave an interview. Hassabis is the CEO of DeepMind, Google's flagship AI research division, responsible for Gemini and several other breakthroughs. But he's not just an executive. He's a practicing scientist and the 2024 Nobel Prize winner in chemistry for AlphaFold, the neural network that cracked protein structure prediction. His estimate was cautious, but revealing. Hassabis believes it will take another 5 to 10 years to reach AGI, artificial intelligence, capable of learning and performing tasks at a broadly human level. And before that happens, he expects at least 1 or 2 breakthroughs on the scale of the transformer architecture itself, the very foundation of today's generative models. This aligns almost perfectly with Sutskever's message. Scaling alone is no longer enough. Progress now demands new theory, new architectures, and new learning paradigms. And judging by recent developments, Google seems to be taking this seriously. The company is visibly increasing its investment in foundational research, including early attempts to implement continuous learning systems. At the same time, Google CEO Sundar Pichai gave an interview to the BBC. If you haven't seen it, don't worry, you haven't missed much. Even the Pacific Ocean contains more substance. The interview was polished, careful, and almost entirely devoid of concrete statements. But even in an ocean of carefully chosen words, you can still catch a fish. And in this fragment, it becomes clear what Google is really betting on in the coming years. There is progress. I think we have the most advanced quantum computing developments in the world, and the progress is very impressive. I would say that quantum computing is where artificial intelligence was 5 years ago. So I think that in 5 years, we will experience a very exciting phase in the field of quantum computing, and we are investing with that in mind. But, as you know, nature and the universe are fundamentally based on the principles of quantum mechanics. And I think that creating quantum systems will help us better model and understand nature and open up many benefits for society. The key point here is simple, but easy to miss. Google is not betting solely on software. It is building hardware. Not just custom chips and data centers, but something far more radical: quantum technologies. In December 2024, Google unveiled its Willow quantum chip. On a narrow but well-defined class of problems, Willow completes calculations in minutes that would take a classical supercomputer roughly 10 septillion years. Not 10 million, not 10 billion, 10 septillion. A number so large it barely fits into intuition. Hartmut Neven, the founder of Google Quantum AI, believes that quantum computers won't just accelerate existing computations. They could generate entirely new kinds of data suitable for training future artificial intelligence systems. In other words, quantum machines may help solve the very bottleneck that now threatens AI progress: the exhaustion of high-quality training data. Google is not alone in this direction. IBM is actively developing quantum neural networks, QNNs, a hybrid approach where quantum systems are used as learning architectures. Early research suggests that quantum neural networks can possess higher model capacity and better trainability than their classical counterparts. This advantage appears most clearly during training the most expensive and resource-intensive phase of modern AI development. But the implications go further. If such systems mature, they could not only speed up training, but also improve inference, the act of generating answers for users. And more importantly, they could raise the quality of those answers in ways classical architectures struggle to match. This is where the story quietly turns. The future of artificial intelligence may not be decided by larger datasets or bigger data centers alone. It may hinge on a deeper alliance between AI and the very fabric of reality, the quantum structure of the universe itself. I don't want to drown this in technical details, so let's do what works best: use an analogy. Imagine a vast, pitch-black maze. Your task is simple: find the exit as fast as possible. A classical computer behaves like a typical horror movie character. It runs down one corridor, hits a dead end, turns around, tries the next one. Again and again, step by step, trial and error. It works, but it's slow, exhausting, and brutally inefficient. A quantum neural network behaves very differently. It's as if the entire maze is suddenly flooded with water, and the water finds the exit instantly along all possible paths at once. That's the essence of quantum superposition. This isn't science fiction. It's already being used in pharmaceuticals. Teaching a classical neural network chemistry is like trying to explain the taste of an apple using a spreadsheet. You can do it, but it's painfully indirect. A quantum system doesn't describe a molecule. It simulates it, atom by atom, bond by bond. It creates a true digital twin. As a result, it can predict drug effectiveness with up to 85% accuracy compared to roughly 30% for classical models. In everyday conversation, the difference is subtler, but just as important. Take a simple word like key. It can mean a door key, a wrench, a water spring, a musical note. A classical language model has to analyze the entire conversation, calculate probabilities, and sequentially eliminate meanings until it lands on the correct one. That process consumes enormous computational resources. In a quantum state, the word exists in all its meanings simultaneously. The context doesn't filter them one by one. It collapses them instantly into the correct interpretation. The result isn't just faster responses. It's responses that feel more precise, more natural, more human. You know that moment when someone has barely started a question and you already know exactly what they mean and how you're going to answer? This is very close to what's happening. But the real difference between classical neural networks and quantum ones lies deeper in how they relate to reality itself. A conventional neural network is, at its core, statistical. It looks backward. It analyzes the past, extracts patterns from existing data, and then uses brute force probability to guess the most likely outcome. A true quantum network works differently. It doesn't just extrapolate the past. It models the evolution of events. It explores possible futures and selects the scenario that best aligns with a desired outcome. This is where the real magic of quantum technology lies, the reason humanity is so eager to get its hands on it. So what does this actually mean for an ordinary person? It could mean medical diagnostics with unprecedented precision, truly personalized diets with predictable, measurable results. The ability to test how specific drugs will interact with your body before you ever take them, eliminating side effects instead of reacting to them after the fact. Logistics optimized down to the minute. Routes, flights, transfers, delays, all calculated as a coherent whole, not as isolated guesses. It could mean education tailored not just to your level, but to the way your brain actually learns. Custom explanations, visual metaphors that stick. Techniques designed specifically for your memory, attention span, and intuition. And interfaces will change too. Devices will no longer respond only to explicit commands. They will react to meaning, intonation, context, and intent all at once. Not what you say, but what you mean. It's important to be honest here. This isn't tomorrow. The nature of quantum computers is such that for at least the next decade, their use will be economically justified, mostly in large commercial and scientific settings. But that's how every major technology begins. From there, gradually and almost certainly, through subscription-based cloud services, it will trickle down into everyday life. At this point, it may seem that the recipe for AI's future is obvious. More research, quantum computing, faster training, cheaper inference, better data. Problem solved. But the future has a habit of surprising us. 10 years ago, we were told that automation would primarily replace couriers, loaders, and drivers. In reality, it's entry-level programmers and designers who are now quietly packing their bags. We once believed phones would become smaller and smaller. Today, oversized slabs that barely fit in a pocket dominate the market. Progress rarely moves where we expect it to. And artificial intelligence is no exception. Predicting the future is never straightforward. And that's precisely why some companies believe that the future of computing may look nothing like what we expect. One of them is an Australian startup called Cortical Labs. In March 2025, it crossed a psychological threshold by introducing CL1, the world's first commercially available biological computer. It combines 800,000 lab-grown human neurons with a silicon chip, forming a hybrid system where information is processed through electrical feedback loops between living cells and hardware. The groundwork for this moment was laid earlier. In October 2022, Cortical Labs published a study in the journal Neuron, known as DishBrain. led by Dr. Brett Kagan. The team showed that 800,000 neurons grown in a petri dish could learn to play Pong in less than 5 minutes. For comparison, a classical neural network developed by DeepMind, the same division of Google behind Gemini, required about an hour and a half to learn the same task, roughly 18 times longer. More importantly, this was the first clear demonstration of adaptive, goal-directed behavior by living neurons interacting with a simulated environment. The training principle was surprisingly elegant. When the neurons successfully hit the ball, they received predictable electrical signals, a stable, orderly state. When they missed, the system injected chaotic, noisy electrical input, randomness, uncertainty, stress. Neurons, as it turns out, strongly dislike unpredictability. They actively reorganize their activity and form new connections to minimize this noise, not to win, not to score points, but to restore predictability, to regain equilibrium. They learn not for victory, but for peace of mind. In a very literal sense, this isn't a game, it's survival. I understand how strange this sounds, especially in 2025. After all, artificial neural networks are already defeating professional players in Dota, so why should anyone care about Pong? The answer lies in a single word: energy efficiency. This is where biological computing becomes genuinely interesting. Living neurons consume astonishingly little energy. Estimates suggest that biological systems can be tens of thousands, in some cases up to 100,000 times more energy efficient than the most advanced silicon-based hardware available today. In a world where data centers are running into physical, electrical, and economic limits, that difference isn't a curiosity, it's a signal. The key point is this: neurons achieve results with far fewer actions and dramatically lower energy costs. Silicon chips rely on the movement of electrons, high voltages, rapid switching between transistors. Inevitably, a significant portion of that energy is lost as heat. That's the price of speed in classical hardware. Living cells work differently. They generate and transmit signals through ions, moving across membranes, a subtle blend of chemical and electrical processes. It's slower at the level of a single signal, but vastly more efficient at scale. Modern neural networks are built around dense, synchronous computation. Entire layers of artificial neurons activate at once, performing calculations even when many of them don't meaningfully affect the final result. Biology takes a more selective approach. A real neuron fires only when incoming signals exceed a certain threshold. Most of the time, most neurons are silent, inactive, consuming almost no energy. A biological system processes information only where and when it's needed, and that alone changes everything. The human brain is capable of performing up to 1 quadrillion synaptic operations per second, while consuming roughly 20 watts of power, or about 10 if the person isn't scrolling TikTok. A modern GPU used for AI inference can perform nearly 4 times as many operations, but it does so while drawing around 700 watts, roughly 17 times more energy. Of course, comparing a brain directly to a graphics card isn't entirely fair. They solve different problems in different ways, but as a rough indicator of efficiency, the contrast is impossible to ignore. The result is striking. Biological neural networks don't just learn faster, they do so orders of magnitude more efficiently. And just as importantly, they may be cheaper to scale. Brett Kagan, one of the leading scientists at Cortical Labs, notes that growing 1 million neurons isn't dramatically more expensive than growing 100,000. The cost curve is shallow. At first glance, this might sound like an extravagant, niche experiment by a small startup. In reality, it's anything but. Dozens, perhaps hundreds of laboratories around the world are now exploring biological and hybrid computing systems, quietly, methodically, much like they once did with silicon. The Swiss company Final Spark claims to have reached energy efficiency up to 1 million times higher than that of conventional computing systems. They are already building a biological computing platform and have begun offering access to it through the cloud. Another company, Biological Black Box, has introduced a new generation bio-LLM. According to their data, this system learns up to 1,000 times more efficiently than classical neural networks and can already be used for tasks like image classification and video processing. In early December 2025, the startup Unconventional AI raised $475 million to develop a biological computer, with Amazon among the investors, and plans to raise another $500 million in the near future. This is no longer a fringe experiment. Large corporations, startups, and leading universities are now actively working on biological neural networks and, in some cases, already using them. Especially in medicine and pharmacology, where simulating living systems with living tissue is not a philosophical leap, but a practical advantage. What's striking is that the most pressing questions surrounding biocomputers today are not engineering problems. They are ethical ones. In November 2025, Science published a call for international oversight, signed by 17 leading biologists. The proposal focused on establishing ethical rules for working with organoids, lab-grown clusters of living neural tissue. Should donors of biological material be informed about how their cells are used? What if stem cells later become part of systems designed for weapons development? Is it acceptable to implant human organoids into animal brains to improve performance? Can pain or stress stimulation be used as a training signal? And the most uncomfortable question of all, what if, as complexity increases, organic computing systems begin to exhibit signs of consciousness? These concerns aren't speculative paranoia. Today, organoids typically live from a few days to several months. That means they must be grown continuously in large quantities. At the same time, their internal complexity is rapidly increasing. Some laboratories are already experimenting with systems containing 2 billion neurons. Others are openly discussing the construction of full-scale biological data centers facilities designed to sell living computing power through the cloud. The structure of the tissue is evolving. The methods of interaction are evolving. And sooner or later, the ethical questions will stop being theoretical. Especially when you consider the economics. The neuromorphic computing market is already estimated at around $7 billion. By 2033, analysts expect it to grow tenfold to $70 billion. At that scale, biology is no longer just a metaphor for computation. It becomes infrastructure. Perhaps there is no point in trying to predict a winner in this race, betting either on cold quantum calculation or on living biological adaptability. The history of technology suggests something else. Real breakthroughs rarely come from a single direction. They emerge at the intersection of disciplines, and the future most likely does not belong to one of these approaches, but to their fusion. Recent developments quietly point in that direction. Investments in neurointerfaces, from projects like Neuralink to Sam Altman's backing of similar startups, are not random. They signal a deeper shift, not toward faster machines, but toward a different relationship between computation and life. Imagine systems where quantum processors explore vast landscapes of possible futures, simulating reality at a fundamental level. And layered on top of them biological neural networks, making intuitive decisions, providing adaptability, efficiency, and a kind of understanding no silicon architecture can replicate. This would no longer be hardware, no longer organoids, but a new hybrid form of computational matter. And at that moment, the boundary between humans and their tools may finally dissolve. If computers think using cultivated human neurons, and we expand our own cognition by connecting to these systems, where does the human end, and where does the machine begin? The question of whether a computer is alive would lose its meaning entirely. It would become an artifact of our time, a relic from the era of simple silicon chips. Perhaps superintelligence will not stand above us. Perhaps it will not rule us. Perhaps it will not even confront us. Instead, it may become an extension of our nervous system, a shared layer of perception, reasoning, and intuition, part of how we decide, how we understand, how we act, not something we build, but something we become.